Hi, I'm Jack from the Singapore Institute of Technology, and this is a video we made for an introductory course on developing immersive applications. This video will attempt to introduce basic hardware and software components we need to know about when developing immersive applications. So at the end of this video, I hope that you will be able to firstly differentiate between broad classes of XR devices. Secondly, describe common hardware components in XR devices, for example, in a VR head-mounted display. Thirdly, explain the typical image formation process in such XR devices. Fourth, describe the common software components and software architecture in a typical XR application. As usual, you can navigate to rewatch any of the parts by using the video markers in the timeline below. So, common XR devices. XR, or extended reality, is a term to collectively refer to AR and VR experiences. And depending on whether you accept that mixed reality or MR refers to something different enough to AR and VR, then XR can be thought of as a collection of three categories: AR, VR, and MR. So at the time of shooting this video in January 2023, there exists a large variety of different XR devices today, with varying levels of availability to the common consumer. And today the most common devices for VR include the Meta Quest and HTC Vive series of headsets. And for AR, devices include the Magic Leap and Snap AR spectacles. That being said, AR is currently most commonly consumed through the screens of plain vanilla smartphones with a running camera video feed. For MR, Microsoft's HoloLens is almost synonymous with the term, as they sort of redefined the word when the first version launched. But newer devices are increasingly blurring the lines in this space, for example with the new Meta Quest Pro. As you can see, most of the devices mentioned are some form of head-mounted display, or HMD in short. The HMD is hence commonly perceived as the representative device when talking about consuming XR experiences in today's terms. HMDs were originally meant for only VR when they first started, and VR HMDs still remain the most accessible HMD in the market today. In terms of wider availability and the cost of getting one, that is. In general, HMDs for VR can be either for PC VR, with the headgear connected by a cable to a powerful PC, and external sensors for perhaps more accurate tracking, or for standalone VR, sometimes known as all-in-one VR, with no cables and with inside-out tracking. As mentioned, most AR is experienced on mobile phones, and HMDs for AR are still pretty much in its infancy stage. However, newer devices are becoming more and more multi-form for AR, VR, and, if you will, MR. In general, a big part of delivering immersion in HMDs is through a transformation of the visual experience. So let us start from here and understand the optics behind HMDs, primarily from the perspective of common VR HMD setups. First, let's start with the hardware. Here I have a Meta Quest 2 device. I was intending to break this apart and show everything that's inside, but luckily I stumbled onto iFixit and Multiverse's videos here. Without going down to the level of integrated circuit chips, we can see that the Quest 2 basically consists of a display screen, two magnifier glasses, actually on mine there are additional corrective lenses so that I don't have to wear glasses in the device, specialized controllers that emit infrared array lights and have motion tracking sensors to detect these lights, other motion tracking sensors in the headset itself, cameras all over, a battery, speakers, CPU, GPU, a compact motherboard, and typically other sensors you will find on a modern day smartphone. In fact, if we compare the HMD hardware with a modern day smartphone, like the one that's taking the video here, there is a huge overlap in terms of similar components. If you watch a phone teardown video, you can see all the same parts like the battery, motherboard with CPU and GPU, motion tracking sensors, lots of cameras as well, and so on. Of course, mostly these parts are arranged in a different manner to the HMD for obvious reasons. However, a clear difference exists on the HMD, and that is the presence of hardware that allows for appropriate magnification of the screen onto the user's eyes as much as possible to increase immersion. Now let's dive a bit deeper into how some simple additional hardware allows for this magnification to work with the right math, as this is the heart of providing for immersion. So the additional hardware that differentiates HMDs from smartphones is actually nicely packaged into something like a Google Cardboard. So if you have a Google Cardboard, you can actually look at it alongside our discussion here to get a feel for the hardware that we are describing. For students in the SIT DigiPen module, you can get a free one from us. But otherwise, you can buy one for a reasonable price from any of the major online retailers. Or you can build your own one using the open source specifications, although that will really take some time. To start working through the math, let's note some key dimensions and parameters that contribute to the image formation process. In other words, the process of how the eventual magnified image is being formed when we look through the lens to the screen. If we look at the HMD from the side, we can first note the height of the display. Sorry, Leon, can borrow your phone? Okay, so as you can see, I gotten this phone from my colleague Leon at the back over there. And we were talking about the height of the display, which in this case is the phone's display itself when placed on the side in this Google Cardboard setup. So that's the height of this display. And then the other thing we should note is the distance between the display and the lens, which the lens is inside here, and the distance between the lens and the display when placed like that is the other thing that we should note. And finally, we should also take note of what is known as the eye relief when we place our eyes in front of the lens over here. It's called the eye relief, the distance between our eyes and the lens, because it is how much relief you are giving, the eye when defining that distance. With those numbers, we are now going to get a bit technical, but not too much. Well, technical depth is all relative depending on your background coming into this video. If you get lost in the discussion, you may need to get a bit more foundation on the formulations that you are unsure about. If, however, you are viewing this as a DigiPen student from the RTIS or IMGD program, I guess you will have the required foundations and may even want to do some further reading to work out a bit more of the details to convince yourself of the math that goes behind obtaining all these values required for you to generate the projection and look at matrices. In general, we are trying to describe this with the perspective that you have some basic foundation of linear algebra. Using a formula called the Gaussian thin lens formula, given the distance between the lens and the display and the focal length of the lens, we can firstly calculate the distance from the lens to the virtual image formed when your eyes are looking through the lens. With the distance between the lens and the display, the height of the display, and the focal length, we can also calculate the height of the virtual image formed. So there we have the width and the height. To understand the image formation process more completely, in computer graphics speak, there is actually a view frustum created. So this view frustum, it forms a pyramid-like virtual volume containing all the virtual 3D objects in the virtual environment. Note that this view frustum is vertically symmetric meaning that the size and shape of the top half is the same as the bottom half. If we pause here and think about why someone would need to understand it at this level, basically these concepts will become important if you are using a low-level graphics API to generate these images to be shown on the display. For example, if you were to create a projection and view matrices with a library like Three.js, and then applying these matrices to every vertex that define each object that you create in the virtual space, then you would need all this math here. Now, to continue our understanding of the image formation process, let's imagine looking at the HMD from the top, like so. We can note now other dimensions like the width of the real display, as well as the distance between the two lenses that each of our eyes view through, which is commonly known as the interpupillary distance, or IPD. Naturally, the more you can match the device's IPD, or inter-lens distance, to your actual IPD between your real eyes, then the better your viewing experience will be. Here, we should understand how the device's IPD changes the way the virtual images will be formed. With the width of the real display, the screen to virtual image distance, and the IPD, we can calculate the left and right widths . For the left eye, the left widths will be larger than the right widths, and vice versa for the right eye. This results in a horizontally asymmetric view frustum. In other words, this means slightly different images will be formed for the left versus the right eye. Note the difference when we mentioned the view frustum initially just now, that vertically the view frustum is actually symmetric, but now horizontally it is asymmetric depending on whether it's the left or the right eye. So why this needs to happen can be intuitively understood by noting that the eyes are positioned at a horizontal offset defined by the IPD to the center of the virtual world formed. This is also the foundation of how stereo images are formed, and in turn provide a perception of 3D to the human eye. In summary, with the lens focal length, the IPD, the screen to lens distance, and the eye relief, we can obtain all the values that we need to generate the perspective projection matrix that defines the virtual view frustum. In particular, the near and far plane depths, the height, the left and right widths of the virtual view frustum. We can also obtain the values needed to create the view matrix or look at matrix that defines how a camera, in other words our eyes, looks at the virtual frustum. In particular, the values that we get are the positions of the eye and the target position of where the eye is looking at in the virtual world. Again, what all this allows us to do is to directly plug in those values into a low-level graphics library to determine what should actually be displayed on the display screen to create the correct viewing experience from the magnification process. For example, you can plug in dimensions and focal lengths of your Google Cardboard and the mobile that you are placing in there. If you're viewing this video as a SIT DigiPen RTIS student, this rendering exercise will probably be sort of like a no-brainer with your foundations in graphics. For all the rest of us, we can always turn to someone like ChatGPT to further our understanding, if you need so. So with this knowledge, we can hopefully have a better understanding of what changing any of the dimensions or lens properties will do to the eventual viewing experience. For example, imagine if you increased the eye relief, what effects will it have on the eventual virtual scene as seen by the user? Now let's move on to another viewing property of interest that can be calculated. And this property is known as the field of view, or FOV. Using standard trigonometry, given the IPD and distance from the eye to the virtual image, we can actually derive the angles representing the vertical and horizontal FOVs for each eye. The vertical FOV is pretty straightforward as, the top and bottom halves are symmetric. But for the horizontal FOV, we need to calculate the different angles representing the nasal FOV or the FOV on the nose side, okay, and the temporal FOV or the FOV on the temples side. Remember that the view frustum is asymmetric horizontally, and so the viewing cone will slightly be skewed depending on which eye you are referring to. So differentiating or segregating the FOV into nasal and temple angles, this also allows us to determine what are commonly known as the binocular FOV and the monocular FOV. So the binocular FOV, as the name implies, is the combined visual span, right, from the overlapping region as seen by both eyes. And the monocular FOV is also a combined visual span, but seen individually by, the non-overlapping areas, separately seen by each eye, like the peripheral regions. So by this point, you may realize it is rather hard to follow this if you are listening to the podcast version of this. So you should certainly look at the video version of this at some point later so that you can better comprehend everything that is described here, with the visuals included in the video version. Understanding how the different FOVs are generated further allows us to appreciate the design of the hardware in a deeper sense and also arms us with better knowledge in designing the immersive applications that make use of similar hardware. However, do be aware that the FOV is also affected by individual differences like age and visual disorders. The last thing that we will talk about for hardware will be lens distortion. Ever wondered why when we look at the rendered VR view of Babylon JS or A-frame on our phone screens, without the cardboard itself, it looks distorted? Actually, the rendered view has incorporated distortion correction algorithms to counter the natural distortions introduced by the physical properties of the lens. If there was no distortion correction, and you looked at, for example, a regular grid pattern through the lens, the manner in which images are distorted becomes much clearer. Without delving into the math, the further the point is from the center, the more it needs to be shifted in order to counter for the distortion introduced by the curved lenses. Note that other than lateral image distortions, there may be other artifacts introduced by the properties of lenses, like for example chromatic aberrations, which are color artifacts due to how different wavelengths of light refract differently as they pass through the lens. For more detailed explanations and visualizations on the topics discussed for the hardware here, you can actually view Stanford's publicly accessible lecture notes on display optics in the links in the video description and podcast show notes. So what we've described here is what most typical VR HMDs will have in order to provide what has become of an expectation of what a basic level of VR immersion entails. Many other advancements are slowly creeping to become more accessible as consumer HMD hardware in order to potentially improve immersion. Significant advancements in this space include the addition of more trackers on the body, like the Vive trackers, to translate motion from other parts of your body into the virtual world, as well as the inclusion of eye tracking to enable eye-gaze interactions and also something known as Foveated rendering, which both improves performance by rendering less in our peripheral viewing regions, and also improves immersion by enabling more accurate depth of field effects, like how the iPhone portrait mode does in my Bcam over here. Also note that although we have focused on HMDs as a way to discuss specialized components that uniquely target immersion, immersive applications are not just delivered through the type of hardware that we discuss here. In fact, if we take a broader view of what immersion is, this type of experiences may not even require a screen, but I'll leave those discussions for another time. For now, let's move on to software and talk about common core software components we see in immersive applications. Most immersive applications at its core is basically an interactive real-time simulation. When looking for resources to understand these core software components that we will talk about, it may also be helpful to look at what makes up game engines instead, which can be viewed as a specialization of interactive real-time simulations that also has a focus on providing playful and joyful experiences. So let's start here and look at what are the typical software components that make up interactive real-time simulations like game applications. This includes a rendering system, a physics system, an input handler, an audio processor, and an AI system. So these core components may take on different names, so perhaps the more important thing here is to understand their roles in providing for the desired immersive experiences rather than their specific names. As our videos are more focused on developing the immersive applications themselves and not the enabling technologies, we will describe these components from the perspective of using the associated functions where available from the libraries and frameworks that you choose to build your immersive applications. In other words, we are not aiming to introduce low-level concepts to build these underlying components, but to introduce the necessary concepts to use these components. First, the rendering system. As the name implies, it is responsible for drawing all the graphics displayed on the screen. In the first part of this video, we talked about how the virtual images are formed on HMDs via the optical mechanics provided by the hardware components. The rendering system is the component that will help us actually produce these stereo images eventually. However, before we get to that point, there is a fair bit of work for us to do with the rendering system in order to create the entire virtual environment to be rendered. This includes adding 3D model meshes and their associated textures as components in our object representations, configuring the lighting in the 3D scene, configuring the camera component that represents the user's viewpoint, and potentially setting up other post-processing parameters like bloom and depth of field. The actual creation of the content, for example, the 3D models and textures, is beyond the scope of this video, but will be touched on in an upcoming video soon, with a focus on creating content for immersive applications. Note also that we have described operations that we have to directly work with on the rendering system when we build immersive applications. Beneath these direct things that we do with the rendering system, there are loads of underlying lower level operations behind the scenes that enable these operations to function, like scene graph traversal, culling, clipping, shader execution, and rasterization operations, just to name a few. In terms of functionality related to developing immersive applications, most modern full-fledged game and simulation engines like Unity and Unreal already include direct functionality that cater for rendering such graphics meant for immersive applications, like creating stereo images like what we saw earlier. This is also a form of testament that immersion is becoming more mainstream as part of building real-time interactive software. On to the next component, physics. The physics system takes care of the math needed to implement behaviors of objects that simulate the real-life versions of those objects in motion. For example, a simple ball dropping off the edge of a table requires using physics equations involving displacement, velocity, acceleration, and gravity to compute the necessary values to affect the motion of the ball through transformations applied to it at each frame of the simulation. As developers, our role is mainly to attach particular physics components like rigid bodies to target objects that need more realistic behaviors that conform to real-world physics, and then potentially use the API functions to control various aspects of the behaviors. For example, a very common basic functionality is for us to specify response behaviors whenever a collision event happens between two objects that have physical properties attached. Now on to the audio processor. The audio processor is responsible for playing audio and managing audio assets in the application. This includes loading and decoding audio files that can be played by the audio hardware available in the device, managing the playback of typically multiple different audio sources set up to run at different times, maybe at different volumes, pitch, and spatialization, etc. And also to mix these audio inputs to render sound appropriately based on the hardware available. As developers, our interaction with the audio processor mainly involves attaching audio sources to different objects in our application and then calling the required API functions to load audio assets to these audio sources, and then using other functions to manage the playback, for example, and mixing of these sources. Next is the input handler. The input handler processes inputs from various sources and is responsible for identifying and managing these inputs appropriately based on what hardware is available. This is especially important when we aim to create more accessible, cross-platform immersive applications that can cater for a multitude of devices that have different forms of input devices like the keyboard and mouse, touch screens, motion sensors, and specialized controllers for different HMDs. The input handler will capture input events through the operating system that has the necessary firmware drivers to connect to this input hardware. As developers, our main task is to then attach controller components to objects, with these controller components configured to map different input events to specific actions in the application. Like, for example, writing code to associate the trigger button of a Vive controller to a grabbing action in the virtual environment, or associate updates of the spatial position of the HMD to a relative position of the virtual camera in the virtual environment. Last up, we have the AI, or artificial intelligence system. So in general, the AI system of an immersive application facilitates the development of automated behaviors in an animated game object. In general, the AI system of an immersive application facilitates the development of automated behaviors in animated game objects. For example, humanoid characters as part of a simulated workplace training scenario. Depending on the requirements, the level of intelligence that these automated behaviors need to exhibit varies widely, and many aspects of digitally creating these behaviors or digitally recreating these realistic behaviors is an open research problem. The kinds of features available in typical real-time simulation libraries and frameworks hence also vary pretty widely, but typical functionalities are pathfinding algorithms, mostly based on a class of algorithms called A*, to handle navigation across the virtual environment, which may be dynamically changing. Next, decision-making tools like the ability to create finite state machines or behavior tree systems to allow virtual characters to make choices based on the simulated state, their characters' goals, and other factors. Then we also may have learning mechanisms like the ability to configure a reinforcement learning algorithm to allow for the virtual characters to adapt their behaviors over time based on intended reward mechanisms. So our role as developers is hence to attach the appropriate versions of these AI components, like the pathfinding component, to objects that require the particular AI behaviors to occur. So in sum, everything that we have described above are just but a sampling of common software components that we will find in typical immersive applications. Depending on your unique requirements, there may be other components that you will need to incorporate in your application, like for example, a networking working component to handle the data and connections needed across multiple client devices that your application resides on. The various core components that we have described can mostly be implemented using libraries and frameworks that already exist, like those provided by Unity, Unreal, Babylon.js, or A-Frame. To organize your code on top of these components, you certainly need to have a structured software architecture that puts together everything into an immersive application. A very popular architecture pattern is the Entity Component System, or ECS architecture. So in view of the architecture, in a nutshell, your role as a developer is to create all the entities or objects required to build the virtual environment that the user is supposed to interact in. And all the components that we have described above are like ingredients that you can configure and use in your entity concoctions, which essentially means that entities are made up of collections of differently configured components as described above. And finally, the systems part of the ECS are the underlying engines that processes each one of those configured components to eventually collectively realize the required state changes and behaviors that the users will experience in the virtual environment. In fact, most popular full-fledged game creation tools already enforce this architecture. For example, this is how Unity structures its graphical user interface for developers to build their applications. For further information on ECS, you can perhaps refer to the multitude of other videos that describe this in much more detail. With that, we come to the end of this video, and I'll see you in the next one.